All right, this is 3.5-Lewis structures. So we're going to talk a lot about bonding between nonmetals in this section and how two nonmetals can come together to form a molecule or a compound. So the Lewis dot structure is simply a technique used to visually represent the number of valence electrons an element has. So we're going to take a look at four different types of, actually let's go ahead and look at eight different types of atoms, and we're going to draw their Lewis structures. It's very simple to do this when you're just talking about one single atom. So hydrogen, for example, has one valence electron. So to show that, we just put a dot somewhere around the hydrogen atom. You almost make believe like there's a box around that element. There are four sides to that box, and so you can put that green dot on any one of the four sides that you'd like. So helium is the next atom, and helium has two electrons. So we oftentimes put both of those electrons next to each other. So they're both on the same side of the box, and that's actually pretty rare. Usually we separate these electrons, but because helium can only fit two electrons in its outermost subshell, we put them together. If you follow along in the periodic table, lithium is the third element, and it has 3 electrons when it is neutral, and then carbon has 4. Carbon has 4 valence electrons. Okay, nitrogen has 5 valence electrons. And you'll notice that I only double up when I have to. Okay, oxygen has 6. Okay, fluorine has 7. Fluorine has 7, so the lone electron, the unbonded electron in fluorine is right there. And then neon's the final one. We know neon is a noble gas, and so it's got a full outer shell. And if you look on the table, you'll notice that it is in that column with an oxidation number of 0. It does not want to gain or lose any electrons, so it is stable. All right? So those are Lewis dot structures for just singular atoms. And now we want to see how those come into play when actually drawing a shape of a molecule. And so Lewis structures will help us identify how elements actually bond together. So to take, for an example, hydrogen atoms. So hydrogen, as we showed before, has one lone pair electron. Okay, one electron. And in order to have a full outer shell, hydrogen needs to have 2 electrons. And so you could think about, well, what's going to happen here? Well, maybe the hydrogen atom on the left will take its electron and give it to the hydrogen atom on the right. That would cause for an excited hydrogen atom there, but a sad hydrogen atom there. So that's not benefiting both. So that's probably not going to happen. And so instead what happens is we get what's called a covalent bond. And so these 2 electrons are going to share. So I'm just going to draw a line between these 2, okay, to kind of signify that the electrons are being shared. So sometimes the green electron kind of spins around here, and sometimes it spins around here, but all in all, that electron is shared between the 2, and it's shared equally. We learned in the 3.4 video that the equal sharing of electrons is called a non-polar covalent bond. Non-polar covalent bond. So that's what we've got going on here. And so the Lewis structure, if I want to draw the Lewis structure for this compound, okay, it's going to be just a hydrogen atom with a line and then another hydrogen atom. And it's this line that tells the reader, hey, there's actually 2 electrons here, and they're being shared between those 2 atoms. Okay? So once again, this is our Lewis structure for hydrogen. All right, so they obviously get more difficult. Hydrogen is a pretty simplistic molecule. So we're going to look at some other examples here in a second. And we're going to start out with water. And so water's obviously got some more atoms, so it's going to be a little bit more tricky to draw the Lewis structure. So it's not a bad idea to have kind of a list of things to do when figuring out how to draw these Lewis structures. So the first thing that I do is count the total number of valence electrons in the molecule. Oxygen has a total of 6 valence electrons, and each hydrogen atom has 1 valence electron. And as you can see from the water molecule, there's 2 hydrogens. So in total here, ladies and gentlemen, we have 8 valence electrons. Now the next thing to do is connect the atoms. Now, the atom that is less prevalent is usually your central atom. And so we're going to go ahead and toss oxygen right in the middle. There's oxygen. And I said I was going to connect the atoms. Well, if you remember from the last slide, to connect the atoms, we use those little lines, right? So I'm going to do that again. So here's a line to my hydrogen, and here's a line to my hydrogen. And now you're looking at that, and you're probably saying to yourself, well, Mr. Cornick, I was going to do it, but I was going to do it like this. I was going to connect it like that. I want you to take note of something here. Hydrogen, so any hydrogen atom, can only form one bond. And if you'll notice, this is kind of violating that whole idea, because that hydrogen atom is forming two bonds. So whenever we're drawing these things, we want to keep in the back of our mind, well, hydrogen's only ever going to form one bond. And so because of that, that bottom Lewis structure is incorrect. And the Lewis structure that's in purple here is correct. So, okay, so we've done number 1 and we've done number 2. Number 3, I call it happifying. I want to happify the atoms with lone pair electrons. So how do we do that? Well, hydrogen owns or shares 2 electrons. And if it owns or shares 2 electrons, it's happy. Now remember, the bond signifies a sharing of 2 electrons. So there's a sharing of 2 electrons. So the hydrogen atoms are happy because both hydrogen atoms are sharing 2 electrons. So they're good to go. So let's take a look at the oxygen then. So oxygen, how many electrons is it sharing right now? Well, we've got 2 here, and we've got 2 here, so that's a total of 4 electrons. Okay, 4 total electrons. It's not happy. You know, hydrogen needs 2, but all other elements that we're going to work with here need 8. And so what do we do here? We have to add lone pair electrons in order to happify oxygen. And this is what that looks like. So we've got 2 electrons there. That's a lone pair. And that's a lone pair. And so now if we count, we have, let's see, we have 2, 4, 6, 8 electrons that oxygen owns or shares. So oxygen is also happy. So we're good to go. All right. So what you're looking at there is the Lewis structure for water. Now, there's some other steps. If we happify, when we get to the end here, the last thing we have to do, so after we've checked that one, is we have to check the valence total. Okay? So we have 2 electrons, 4 electrons, 6 electrons, 8 electrons. And we have to make sure that the beginning valence and that end valence match up with each other. And in this case, they do. So that means we don't have to do step 5. We're all done at this point. If they don't match up, we have to add something called multiple bonds. We'll get to that in a second. All right, so let's look at another example here. HCl. I'm going to put on the last 2, actually. HCl and NH3. All right, so HCl, that's actually hydrochloric acid. Hydrogen is happified. And now chlorine's happified. Okay, I kind of followed the whole list there. I know I did that quickly, but if you pause the video and kind of rewind, you can figure out how that works. The last one is ammonia. All right, so all the hydrogens bonded to that central nitrogen. Nitrogen needs 1 pair of electrons up top, and that one's happy. So again, you know, you want to try to see where that comes from. Maybe pause the video and look through the rules again. All right, so to move on and just talk about that last step there. Sometimes we have a compound that doesn't add up. So the beginning amount of valence electrons doesn't add up with the end valence electrons. And so multiple bonds are needed in order to make the compound actually work. So I'm going to give an example here of nitrogen. So nitrogen's interesting because nitrogen never hangs out by itself. It's always going to bond with another nitrogen atom. So if we draw the Lewis structure for nitrogen, if we follow the rules, first thing to do is to add up the total number of valence electrons. Each nitrogen atom has 5. 5 plus 5 is 10. So we should end up with 10 valence electrons. Okay. The second thing to do is to connect the 2, just like that. And then to happify. So we want to make everything happy, right? So if you add up the 6 electrons around the left nitrogen plus the 2 from the bond equal 8. Remember, those 2 are shared to the right nitrogen. Add those to the 6 around the right nitrogen. That equals 8. So everything's happy in this case. Then the last thing to do is to go up and add the electrons. And so we've got 2, 4, 6, 8, 10, 12, 14 total electrons in my Lewis structure. But remember, I could only have 10 valence electrons. That tells me that this Lewis structure is actually incorrect. That doesn't work. So how do you make it correct? Well, in order to reduce the total number of valence electrons in your structure, you have to add something called a multiple bond. And in the case of nitrogen, we're actually going to add something called a triple bond. Okay? Now, both nitrogens still need one lone pair of electrons on either side. And then you'll notice that we have 2, 4, 6, 8, 10 electrons in total. And that does, in fact, equal that initial amount. And so this is the correct Lewis structure for the nitrogen molecule. Now, just a short word about multiple bonds is that multiple bonds are stronger, and they're harder to break than single bonds. And so when you have something that's multiple bonded, you know that that compound is going to be pretty stable. You can do a couple more examples. I just did the N2, but you're more than welcome to do the O2 and the CO2 for good practice. Lastly, where does this lead? Well, we can obviously eventually bring bigger and bigger molecules into this. And my favorite molecule is caffeine. And so we can draw like the caffeine molecule here and show that this is a Lewis structure. We can see that there are multiple bonds like that one and that one. We can see that, let's see, carbon has a total of 4 bonds to it. If you count the bonds in carbon, there's 1, 2, 3, 4. It's very common for carbon to have 4 bonds. Very common for nitrogen to have 3 bonds to it. Okay? And so these are the neat, cool structures, the Lewis structures that we can build by understanding this concept. All right, that's 3.5.